Hello everyone, welcome to my Informs presentation. I'm Adib Zaman. I worked with my PhD advisor, Dr. Dongping Du, in my dissertation research. I'm currently with the University of Florida as a postdoctoral research associate in pharmacotherapy and translational research focusing on EHR data analytics. Dr. Du is currently an associate professor of industrial manufacturing systems engineering at Texas Tech University. This research focuses on the application of a robust irregularly sampled time series imputation and a predictive modeling approach with uncertainty propagation to assess the readmission risk for congestive heart failure patient. In this slide, I want to talk a little bit about some background and motivation for this research. According to different sources, congestive heart failure is considered the leading cause of hospitalizations among adults in general. CHF and related diseases are usually difficult to treat due to various factors. That is why there is a high readmission rate, around 50% among the patients after CHF diagnosis. This is a very high percentage, and despite many efforts to reduce the early readmission rate, it has not reduced that much, causing billions of dollars each year. Hospital readmission is directly linked to the service quality of that hospital, so it can be considered as an indicator that the hospital is doing good or not in terms of patient care. To ensure the service quality, Affordable Care Act in 2010 imposes a financial penalty on the hospitals whose 30-day readmission rate is high. To sum up, this research focuses on hospital readmission prediction, which is very high among CHF diagnosed patients. If an early readmission can be predicted well, it may save tons of money and improve the hospital service quality. As we find in many analyses, the temporal information is not considered, but in real life it is necessary to consider the importance of time sequence data. But this is usually very difficult to deal with while there are many missing values associated with the dataset. Some common imputation techniques like ARIMA, EM, GMM, KNN, etc. have been found in the literature, but most of these are not able to incorporate the temporal information needed for our analysis. The usual machine learning based methods do not consider any input uncertainty, but our dataset will have imputation uncertainty which needs to be propagated to the model output. In recent development of recurrent neural networks, several attempts have been made to achieve a better prediction accuracy for rare events. These methods are mostly focused on prediction accuracy but do not care much about robust imputation techniques. Uncertainty propagation with predictive modeling is found in the literature, but they are not usually used for EHR time series analysis. In this presentation, we shall focus on GROD bias methods and the probabilistic SVM method as described in the cited papers. Based on the surveyed literature, two potential research gaps have been identified. The first one is the need for a multivariate irregularly sampled time series imputation with uncertainty estimation method, and the second one is an uncertainty propagation technique integrated with predictive modeling. For the multivariate irregularly time series imputation, we use GROD bias imputation, or in short, GOBI method. The major steps of this method is described in the cited paper. We start off by talking about neural ODEs and recurrent neural networks. Neural ODEs are useful for continuous depth neural networks. This method involves performing a reverse mode differentiation technique that is more commonly known as backpropagation. Recurrent neural networks, or RNN, is a special type of artificial neural network that can exhibit temporal dynamic behavior in sequence data. GRU is a special type of RNN that is much simpler and efficient in some datasets. One of the major advantages of using GRU is that it is quite fast. Two types of GRU cells has been used in this technique, GRU-ODE and GRU bias. The first one integrates neural ODE within a GRU cell, and the second one integrates Bayesian estimation within the GRU cell. Bayesian estimation allows the updating of prediction after the model is run on GRU cells. The most important feature of Bayesian estimation is the ability to incorporate new information as they become available. In this imputation method, only the available values can be used as source information, since the missing values play no part. I apologize for not going into much mathematical details here due to time constraints, but feel free to reach out if you are interested in more technical details. For the predictive model with uncertainty propagation, we chose to use a support vector machine, or SVM classifier. Before using probabilistic SVM, or PSVM in short, there are some additional steps that need to be followed. Since our dataset is not balanced, there is a high chance that the algorithm will not be able to predict the low frequency class, that is the 30-day readmission. To balance out the dataset, there needs to be a sampling process which will allow the random sampling of important samples only. For example, the non-readmitted patients actually form almost the entire dataset, and there are only a few readmitted patients. Now, to achieve 1:1 balance in the dataset, the non-readmitted patients need to be sampled many times, but during this sampling process we want to pick the patients who provide more insights for prediction than the others. To create the ranking, we first cluster all the non-readmitted patients, and then within the cluster use principal component analysis, or PCA, to rank the samples. The samples with higher weight will be picked more during the random sampling process. On the right, there is a summary of what I talked about. As you can see, the k-means clustering and the PCA-based sampling technique were only applied to the non-readmitted class samples to achieve a 1:1 balanced dataset. Here is the formulation of the probabilistic SVM proposed by Lee et al. In 2012. The constraint on the standard SVM and the probabilistic SVM remains somewhat similar. The significant difference lies in the objective function. In standard SVM, the objective function is to minimize the square of the separating margin and the standard error. In PSVM, the objective function is to minimize the expected value of the separating margin using the PDF of the inverse of the separating margin, which is calculated from the dataset. You'll find more details in the cited paper. As for the constraints, PSVM follows the standard SVM. Medical information marked for intensive care, or in short MIMIC3 version 1.4 dataset has been used in this study. Let me tell a little bit about the dataset. MIMIC3 is a very large database of 46,520 unique ICU patients who were diagnosed in Beth Israel Hospital in Maryland between 2001 and 2012. There are 58,976 admission records in total. In order to access this database, one is required to complete a course, achieve a certificate, and request the access on PhysioNet website. The database is built on 26 distinct tables that contain de-identified electronic information about ICU patients. It also contains billing information, drug prescription, doses, discharge information, and so on. However, like any other electronic healthcare record databases, MIMIC3 also have numerous missing values that it might go as high as 80% in some cases. So it is very difficult to train any model in this kind of incomplete dataset. Our patient cohort involved CHF and other CHF related diagnosed patient, which totals to 10,027. For a readmission, we only considered the patients who has been readmitted at least once and only kept their first readmission record. The non-readmitted patients or patients who have not been followed up were kept as usual. In our study, we used a combination of categorical and numeric features. The categorical features had lower missing percentage than the numeric ones, and so we coded the missing values in case of the categorical features. For the numeric features, we used the GOBI method for imputation. The numeric features include heart rate, respiratory rate, arterial blood pressure, prothrombin time, etc. At the bottom of this slide, we show the data summary from MIMIC3 database. As seen in the slide, the bold mark tables were used in this study. If you'd like to have more information on our patient cohort and MIMIC3, please reach out and I can try to help you. These are the imputation results. Let me explain the different axes in these plots. Along the horizontal axis, we have the hours from discharge. So we only consider the measurements before 48 hours of discharge, as you can see from the plots. So along the horizontal axis, the more recent values are to the left, if you are to consider the time when the measurements were taken. It might be a little bit confusing to understand, and so I've tried to explain it in my talk. Next up, the vertical axis is business as usual and represents the actual measurements. The different colorful solid lines represent the imputed values, and the colorful dots represent the observed values. The red dashed line represents the 2 sigma upper and lower bounds of the predictions. Here we show results from the 3 features: arterial blood pressure systolic, heart rate, and arterial blood pressure diastolic. We got a lot more features than this, but we just showed 3 in here. However, we are currently investigating on the zigzag pattern that is shown in this plot. One possible reason could be the weight between GRU and Bayesian update while calculating the loss function. In this plot, the Bayesian update seems to be more in control of the prediction rather than the GRU. We plan to explore more in this area. In this slide, we report the performance comparison between the GRU-OD bias imputation, or in short, GOBI method, and other well-known time series imputation methods. We classify the methods based on their type. One is a baseline method with no recurrent neural network. Mean and median imputation fall into this category. Grand mean and grand median have been used to impute the dataset in this case. The RNN-based methods are more robust but usually need more time and heavy computation power. However, the RNN-based methods used here as are recurrent imputation of time series, or RITS, which is a bidirectional variation called BRITS. GOD is another method proposed recently and provides great predictive results. mRNN is a short form of multidirectional RNN. mRNN is a multimodal neural network mostly used for image classification. It shows good result, the second best one in this experiment. GOBI is the method that is described here and clearly shows a better imputation performance than the others. However, it should be noted that most algorithms used here have been repurposed for imputation tasks. Initially, they are poised to predict but not explicitly impute data. We report root mean squared error and mean absolute error here. These are absolute values, not the scale ones. So now I shall talk about the comparison between various state-of-the-art methods for predictive modeling. I classify them into 2 categories, deterministic and probabilistic. Since the dataset is not deterministically imputed due to numerous missing values. It is more appropriate to compare between probabilistic approaches, but there are not many well-established methods for uncertainty propagation in this case. So here, the main value is used as the imputed value for the deterministic methods. However, please note that the time series imputation was only applied to naive Bayes and probabilistic SVM methods. As you can see from the plot, both logistic regression and PSVM show good performance on the dataset and provides very close prediction. But logistic regression uses more of a static dataset, which is not totally appropriate for this kind of analysis. The other methods usually fell behind these two methods. We are currently investigating if results could be improved further by PSVM. We're currently working to see if we can further improve the PSVM results by finding our sampling or clustering methods and using more robust modification in the PSVM formulation. So far, we have presented a multivariate irregularly sampled time series imputation for EHR and an effective uncertainty propagation model to assess the readmission risk of CHF patients. The research implication of this study can be broad. Multivariate time series imputation is vital for complex processes. This study reveals that the time series sensitive data imputation is quite challenging and many of the well-established methods are not yet capable to handle it properly. Multivariate imputation and prediction with uncertainty can be used not only in EHR data analysis but also in retail, marketing, industrial applications, and many other sectors. Last but not the least, our work has been generously supported by TTU IMSC, Edward E. Whitaker Jr. College of Engineering at Texas Tech, and National Science Foundation. Thank you so much for listening to my talk. I believe this research will be helpful for people working on EHR data analytics or time series analysis overall. So feel free to reach out if you need any help. If you have any questions, please feel free to ask now or reach out at adib.zaman@ttu.edu. I shall be very happy to answer any questions you have. Thank you.